Welcome to GoToWebinar, Web Events Made Easy. Welcome to the webinar. You have entered as an organizer and may now speak to any other organizers or panelists on the line. When you are ready to begin the presentation, press the Start Broadcast button on the GoToWebinar control panel to allow all attendees to hear you. This system will notify you once you begin your broadcast.
Welcome to the webinar, An Introduction to Multivariate Analysis with the Unscrambler X. Presenting today is Dr. Catherine Bakev, Camo's Chief Scientist for North America. Catherine holds a PhD in polymer science and is a recognized expert in spectroscopy, chemometrics, and has a wealth of experience in multivariate analysis. We have a number of people registered today, so if you'll just be patient while everyone gets logged in. But while we're waiting, I'll take a moment and tell you a little bit about Camo. Camo is the oldest commercial supplier of multivariate analysis software. The company was established in 1984 in Norway by a group of scientists who developed the software for clients in the food and beverage, the oil and gas, and the pharma sectors. The first commercial release of the Unscrambler was in 1986, and in 2010, Camo celebrated our 25th anniversary with the Unscrambler X suite of products. In January of 2011, we unveiled version 10.1, a fully re-engineered version of the Unscrambler. Our product portfolio includes our flagship product, the Unscrambler X for multivariate analysis, which also includes design of experiment. The Unscrambler is suited for a wide range of data analysis tasks such as exploratory, regression, classification, and prediction. We also have a complementary software which allows the use of the Unscrambler models to be developed and deployed in real-time analysis in a production environment. In addition, Camo has a full range of professional services, including consultancy to assist in building models, and we also offer options, a host of training options in multivariate analysis, as well as a complete range of IT solutions. Over the years, Camo has grown into a global organization with our corporate office located in Oslo, Norway. We also have operational and support offices in New Jersey, in Woodbridge, New Jersey, to service North American markets, and additional support offices in Yokohama, Japan, Sydney, Australia, and our R&D is located in Bangalore, India. This really gives Camo genuine global reach and the ability to service our clients wherever they are. Originally, multivariate analysis was used by research and process industries, including the pharma and chemicals, energy, and food and beverage. But over the past few years, multivariate analysis tools have been used for data mining and better predictive models as businesses realize there is enormous value in their data. In fact, the Unscrambler was even used by NASA on Mars for the rover Curiosity for classification of rock samples. I have up here just a list of some of our esteemed clients, so lots of experience in all various different industries. And with that, I'm going to turn it over to Dr. Bakev.
Hello everyone, welcome to today's webinar. I'll be covering today a brief overview of multivariate analysis and then some examples and theory on principal component analysis and partial least squares in the Unscrambler X. As Tracy mentioned, we launched version 10.1 in January 2011, and that will be the basis of today's hands-on work with the Unscrambler. To begin with, I'd like to mention a little bit about our philosophy at Camo. Our philosophy is to provide you with the tools to analyze your data regardless of the structure of your data. And those tools are those that can be used for scientists across many different areas, allowing you to do the essential analysis, starting with exploratory analysis, and allow you to visualize your results. We offer the basic tools such as principal component analysis and partial least squares, as well as extensive specialized methods that are used more in expert levels. An important part of multivariate analysis is that our models are data-driven. Therefore, it's extremely important that we validate our models with independent data, and the Unscrambler allows you to validate your models at different validation levels. We also provide training where available for the methods that you use to help you in solving the problems that you're dealing with. So why is multivariate analysis needed? Here I show a picture where I have two control charts, univariate control charts, one for temperature and one for pH, where I have 100 measurements for each one of these variables. And we see that everything seems to be fine for both the temperature and pH when we look at them univariately, and I do have on these lower and upper limits. But when we look at these in the multivariate sense, as plotted in the upper left corner, we see that the point in red is actually not following the same correlation structure as all the other samples are. And looking at a schematic of such a point in the other plots, there doesn't seem to be any issue with that sample. But it's only when we look at things multivariately that we see that there may be a problem with a particular point because the correlation between these two variables, which do have a relationship, has broken down for that point. So multivariate analysis allows us to understand the relationships when we have more than one variable and to indeed see when those relationships or correlations break down. We need multivariate data analysis because indeed real-world problems are multifactorial. We have many different types of data which have many variables. This can include process data, census data, instrumental data, a whole host of the types of situations that we are faced with in doing our work and going through our lives. And these multifactorial problems need multivariate mathematics, including regression, to enable us to identify, extract, compress, and exploit the underlying structure in our data, and to help us to visualize that. So multivariate data analysis, which we term chemometrics when we apply it to chemical problems, enables us to have an overview of complex problems by finding the latent variables, the principal components or PLS factors, that give simple models from these complex systems. It enables us to have an interpretation of the relation between our samples and variables, see the qualitative structure-activity relationships, and indeed visualize our data, which otherwise may be very difficult to look at in large tabular formats. There are many types of multivariate data. These can include instrumental data such as spectroscopic data, chromatographic data, imaging data. It can also include process data where we may have many different types of univariate measurements that we've made, such as the pH and temperature I previously mentioned, and other variables that we're measuring that are actually interrelated. So we would get more from the data by looking at it in a multivariate sense. Sensory data, which can entail descriptions by panelists and instrumental information about products which we want to relate to perhaps product quality or consumer preference, is multivariate, as is product data, information about the different properties and prices of products and the buyer preferences and demographics. We use multivariate data analysis in many different types of situations to look at complex problems. This can entail design of experiments where we're looking at formulation, product and process development, optimization, process monitoring, analysis or exploration, which is qualitative data analysis, or indeed quantitative analysis, which enables us to do model predictive control modeling. There are numerous data analysis tools for different purposes, including experimental design, or DOE, which helps us to bring a focus on valuable information and find the significant effects between different inputs and outputs in an efficient manner, which allows us to reduce the time and cost of our experimentation. Exploratory data analysis tools such as PCA, cluster analysis, and multivariate curve resolution allow us to describe the structure and quality of our data, looking at just one block of variables, such as perhaps spectral data or metabolomic data, where we'd like to see different clusters of samples, see how they are similar to each other. So we get a map of the samples, which in a PCA analysis would be a scores plot. We can see then the groups, patterns, and outliers of our data, and from this exploratory analysis, maximize the insight into a data set. We also have classification and discrimination tools, wherein we would develop models based on the different classes or groups of samples, and then use those models to classify or discriminate new samples into these modeled groups. When we're interested in quantitative analysis and being able to predict quantitative values, then we use regression methods, which may include multiple linear regression, principal component regression, or partial least square regression. Here we're looking for the relation between two blocks of variables, our x and our y, wherein we want to then model the relationship to develop a model so that we can then make indirect measurements, applying our model to new x measurements to then get the predicted y value. So now I'd like to talk about some of the mechanics and basics of multivariate analysis within the Unscrambler, beginning with collecting, importing, inspecting, and preparing our data. Now, those of you who have done quite a bit of analysis can already appreciate the fact that these mechanical steps are very important and quite time-consuming in our analysis. It's said that we spend more than half of the time in data analysis in preparing our data for our analysis, and this is time indeed well spent because it can help us in being able to interpret our data more readily. One of the important things is indeed which data to use in our analysis. We need to have representative data. We need to have samples that are representative with respect to the properties that we're interested in measuring, spanning the range of measurements we're interested in, including the variability that may exist in our process or products, and having enough samples to truly represent the population that we're looking to measure. Now, there are no strict rules on how many are enough samples, and depending on the complexity of your situation, you may need many, many samples, or if you have a very clean system wherein your measurements are very straightforward, you may need just an even distribution of samples across the range of concentrations, perhaps, that you're interested in measuring. We may have an interest in having a general model, a model that can apply to the full population of our samples, whatever that population may be. Herein we would include extreme samples, or we may be more interested in a robust model, one that is more representative of what is typical of our population, so perhaps our normal operating range. And here we have two schema of what these might be. So for a more robust model, we may have just samples in this normal operating range, whereas for a general model, samples spanning into the extremes of the ranges. An important point is indeed that garbage in gives garbage out. This adage really holds true when we're doing data analysis. No software, no equation can give you an answer where there isn't a true relationship within your data. So you have your data, and now you'd like to begin your analysis within the Unscrambler. And indeed, one of the first steps is importing our data into the Unscrambler. And you see here under the File, Import Data menu, there are a whole host of different file formats that can be directly imported into the Unscrambler. So we can also use copy and paste from Excel, as well as a drag and drop from some of these other file formats. But we need to get our data into the Unscrambler and organize it for our analysis. Once our data have been successfully imported, we want to organize our data into column sets and row sets. So the row sets would be the organization of our samples by our rows, so the organization of the samples, and columns are indeed the different variables. So we would use the define range dialog to enable us to do this organization of our data. It's also important that we visually inspect our raw data, making sure that our data integrity has been maintained and that our data are as we expect them to be. So it's very good to plot our data in different ways that are representative of it, and you have the ability to make multiple scatter plots, making line plots, which is quite appropriate for spectral data. You can also look at histograms and other types of plots to look at the trends and patterns of our data. It's important to look for the data structures, and indeed in this group of spectral data here at the bottom, I've highlighted where there seems to be a problem with one of the samples where there's a spike in the data. And it is important that indeed we look at our data before we dive into our analysis. It's also helpful to make histogram plots, especially for our response variables. If we're looking to develop quantitative regression models, we actually do want an even distribution of our samples across our range of interest. When we plot a histogram plot, it is shown with the normal probability curve superimposed on that. And for some types of analyses, we are interested in a normal distribution of samples. And indeed, with regression, we're interested in a normal distribution of the residuals of our analysis. But when we want to do a regression, we want to have what is called a boxcar distribution of samples across our range of interest. And that's what I have exhibited here in the histogram plot on the right. Another useful way to explore our data before we get further into our analysis is to do descriptive statistics. By going under Tasks, Analyze Descriptive Statistics, we get a quantile plot, which is a box plot showing the minimum, mean, and maximum value for each one of our variables, as well as then the 25th to 75th percentiles values. So this is a good way to understand the values within our samples and understand if we perhaps may have some outliers, or indeed here as well we can do some grouping of our data to see if there are patterns in it. Category variables are a type of variable that's quite useful in helping us to visualize our results, and is also something that we use when we're interested in classifying samples, something that is beyond the range of today's webinar but we'll address at a later webinar. If we have category variables within our data, here I have a column wherein the category variables are actually the names of different raw materials for which I have the near-infrared spectra. I can then use this information to color code my plots, which is what I have exhibited here. I've used sample grouping to code my spectral data as well as my data in my PCA scores plot by the different categories, and I see that I have distinct groupings of my samples in the raw data as well as in my PCA analysis. Sometimes we do need to modify our data to help accentuate our ability to analyze it. In this case, we apply transformations to our data, and this would be under the Tasks Transform menu. And there are different transformations that we may want to apply. For spectral data, we may want to add derivatize our data or apply scatter corrections. We may want to standardize our data to give variables an equal weight. That would be the case when we have process data or data that comes from many disparate sources. For separations data, we may need to do some alignment along the x-axis, wherein we can apply a correlation optimized warping. Or we may apply a log transformation to mass spec data so that we don't have overwhelming signal that dominates in our analyses. So to apply transformations in the Unscrambler, we go to Tasks, Transform, and we see a large selection of different transformations that can be applied in the Unscrambler. So now I'd like to revert to our software to show you some examples of what I've been talking about. I'll show two examples of importing data and organizing it into the Unscrambler. So let me now revert to the Unscrambler, which I have here opened. And this is the main user interface for the Unscrambler X. So I'd like to begin by importing data. So I'll begin by going File, Import Data, and the first data I'm going to import is from an Excel spreadsheet, and I have this data here called Euro Work, and I get a preview window of what is in this spreadsheet, and if I had different sheets I would be able to choose the different sheets, but here I can choose to import all of the data or just some of the data, but here indeed I'm going to import all of my data. Oh, let me just highlight it all. And clicking OK, my data are then imported. And you see that I have data here in the lower right corner. I see the dimension of my data is 26 rows and 10 columns. This first column, called region, is shown here as a text data type. But I'd like this to be a category variable, where this category is describing which region of Europe these different countries are located in, be it north, south, east, west. So to change my data type, I highlight my column, I right-click and choose Change Data Type, and I change that to Category. I have a category converter, wherein what I'd like to do is make new levels based upon the individual values in these cells. So clicking OK, I now have this column in orange, because it is a category variable. My other columns, I will use my define range to open my define range dialog, and I will call these columns my GDP values. So what I've now done is I've created a column set. So in my project navigator here on my left, I have my data matrix, Euro Work, which I imported, and I see that I've now created a column set called GDP values, and you see there's a little lock here. I can't modify this column set if I want to make any changes to my data organization. I need to come up here to the mother tree. So that's importing data from Excel. We can also do some quick descriptive statistics on these data to get a sense of what these values are. I could do histogram plots of these data. By highlighting all of these, I choose histogram. And now I have the histogram plot here for the variable agriculture. So I see that I have one sample with a much higher value than the others. If I scroll through here, I can see the histogram plots for my different variables. I can do descriptive statistics as well, again highlighting these columns. I can come to tasks, analyze descriptive statistics. Applying this, I see now I have a new node in my project navigator called descriptive statistics, and I have my plots here, my quantiles plot, my mean and standard deviation. So it looks that I have an extreme sample in agriculture, something I also saw in my histogram plot, and I get a sense of my data. So all good things to do in exploring our data as part of our analysis. Now I'd like to show the import of some spectral data, coming File, Import Data, and I have many different formats here, some which are proprietary instrument formats, and I'd like to actually use one of those today. It's the Omnic software, and I have some data here. These are near-infrared spectra of ethanol water mixtures, so I'd like to import these data. If I click and choose my first file, I can then choose Auto Select Matching Spectra, and it then shows 29 samples that I have in this designated folder. I can get a preview of those data, and here I see these are the spectral data that I'm interested in. So clicking OK, I've now imported this new data matrix, and it's given the name of this as my first sample name actually. This is my new data matrix. So these are near-infrared spectra of different ethanol water mixtures. So I can show those to you here. These data I'd like to use to show you how to do regression. So I also want to add here, in addition to the spectral data, I want to add information on what the concentration of ethanol are in these samples. And I have those data in an Excel spreadsheet. So what I'm going to do here is insert a new column into my data by going Edit, Insert Column, one column here. And what I'm going to do is open my Excel spreadsheet where I have the concentration values, and finding that here in my folder. I have my ethanol lab values here. So what I'm going to do is I'm going to copy these values, copy from Excel, come back over to the Unscrambler, and paste those values here. So paste, and now I filled those in, and this column is indeed my ethanol values. So I'll now further organize my data, creating this as a column set for ethanol. Coming again to my defined range, this is called ethanol, and that will be my Y variable for my regression. My other columns are my spectral data, so I'll just select all of these columns by selecting the first column, holding down the Shift key, and moving all the way to the right to column 2001-28, and these are my spectral data. Clicking OK. And I'd also like to divide this into a calibration set, my first 15 samples, so highlighting the rows now, coming to the defined range dialog. These are my cal samples. And I can invert that selection by using that invert selection button up at the top, coming again to the defined range. So these are now rows 16 through 29, and these are my test samples. So that is the beginning of how we import and do some organization of our data within the Unscrambler. So coming back now to our presentation, I'd like to now tell you a little bit about principal component analysis before I do a demo of that. Principal component analysis is indeed one of the true workhorses of multivariate analysis. It's an excellent exploratory data analysis tool which enables us to extract information from our data and remove the noise by going to compute the principal components. And through this we reduce the data dimensionality. So the data structure that we use in PCA is of course consistent with the data structure I've shown you within the Unscrambler, where we have a data matrix wherein each row is a sample or an object, and each column is a variable. And those variables could be discrete values, such as I have in the Euro work data, where there are different values for GDP in different countries, or they can be highly correlated variables, such as come from instrumental measurements, such as the near-infrared data that I also have. So I can have many variables, and actually there is not a limit to the number of variables that Unscrambler can handle. It's really your computing power that's the limitation. So when we do a PCA, we have our data, which we call X, our X matrix, and from this we get a model, a PCA model, which carries the structured part of our data, explaining the structured variance of our data, and then the error, which is carrying the noise, or the really the non-structured part. One of the key outputs of a PCA analysis is a score plot, which is the map of samples. The map of samples can be depicted here, where we have a projection of our original data into our new variable space coordinate system of principal components. And from the location of samples projected into our score space, we can understand something about the similarity or difference of our samples to each other. So samples that are close to each other in a score plot are similar, and those that are far apart are dissimilar. Indeed, within a score plot, we may even see that we have grouping of samples. So samples that are similar are grouped together or dissimilar. And that's what I have shown here in this 3D PCA score plot, which I've color-coded here in green and red respectively, these are data from mass spectrum that are measured on different serums of cells, where some are known to be cancerous. Those are those in green, and those that are control samples. So the PCA analysis allows us with three principal components, three latent variables, to see grouping of data, wherein the original mass spectral data had over 15,000 variables. So this score is indeed the distance from the mean of our sample population along this new coordinate system of a principal component. We also calculate the loadings when we do a principal component analysis, and this tells us the relative contributions of our original variables, mass spectral data, the economic data that we'll show, to the principal component. So we can see how much each of one of these original variables contributes and explains the variance, or is related to explaining the variance in our data set. Now I'd like to go back to the Unscrambler and show you a demo of doing a PCA analysis of the European work data. The data set, which I've already imported and done some organization for, includes data from 26 European countries and the different economic sectors. In the data, we have the percentage of GDP, gross domestic product, that comes from 9 types of activities. Now these data are already quite dated. You'll notice that even from the names of the countries that are listed. But it allows us to use a data set wherein we can see the relationship of the samples to each other and how they vary based on different economic sectors. So coming back to the Unscrambler, I'll come back up to my data matrix here called Euro Work, where indeed these are my 26 samples, 26 countries, and the different sectors, economic sectors. So what we want to do is indeed understand if there are some patterns in these and how they might relate to these different activities that contribute to the gross domestic product of the countries. So we do this by going under Tasks, Analyze, Principal Component Analysis. We define which data matrix we're using. Indeed, it's the Euro Work, and we'll use all of our rows. And the columns, I've highlighted the columns, but I've already also created the column set called GDP values. So choosing that, we have the ability to apply weights to our data, which we will not do here because all of these are on the same scale, 0 to 100. And validation, very important for any chemometric model. So we come to our validation tab, we choose cross-validation, and we have different types of cross-validation methods that we can apply. In this case, we'll use a random cross-validation with 10 segments, meaning that 10% of the samples will be kept out as we go through and iteratively build up and compute our PCA model. Clicking OK, the PCA runs, and then we have the ability to then see our results. When I click yes, it brings up my PCA overview, my results, and it's also added the PCA node here to my project navigator. The key results of our PCA are shown in our overview, but we also have many other results and plots that we could investigate. But we'll focus just today on our scores and loadings plot. The score plot, a map of our samples, is telling us something about the similarity and difference of our samples, in this case different countries. We have information about the different regions from which, of the world or of Europe where these countries are, and I'll add that into our graph by right-clicking and choosing Sample Grouping. And here I can now create different groups based on this category variable, the different region. This allows us to really see some of the patterns more easily in our data. It really is important to be able to visualize our different results, so I can choose the different color coding and so on for these. What I'd like to do is just apply the color codings, leaving the country names intact. So I uncheck the group name as label. Clicking OK, I now see that there is some grouping of the different countries. We see that the Nordic countries seem to be grouped together. Eastern European countries, in a sense, the ones that are in the south, but we see that Turkey is very far away from the other samples. So Turkey seems to be perhaps an outlying sample. We can look at a statistical measure of whether it's outlying by adding the Hotelling t-squared ellipse to this plot. And we see that this sample does fall outside of the ellipse, so it's outside of 95% of the explained variance of our data is this sample here, or I should say confidence ellipse rather. So that is the score plot, the map of our samples. The loading plot then tells us something about the different variables. The relative position of our variables in the loading plot and our samples in our scores plot helps us to relate the samples to the different variables. So we can look at these plots separately in this way, where we can say, oh yes, Turkey has a very large contribution on PC1. A large contribution on PC1 is related to agriculture. Manufacturing has a large contribution on PC2. Samples that are farther along in the PC2 axis of our scores plot have a larger contribution of their GDP coming from the manufacturing sector. We can bring this data information together into a single plot in the biplot. We can do that by going under Plot, Scores and Loadings, and choosing a biplot. And that now puts both our samples and variables together on one plot, so we can put this information together and see it without having to look at it separately. So that's a quick look at doing a PCA analysis within the Unscrambler. So what we saw in doing this, the PCA score plot, a map of our samples, we could see that indeed we have general grouping in terms of the geographic regions, and that Turkey is an extreme sample. I should also mention that the axes, the information on the axes is quite important. This is telling us this first principal component is explaining 82% of the variance of our data. So we have 9 variables that we're looking at in general to begin with, but by doing a PCA analysis, we can explain over 90% of our variance in our data by the first 2 principal components. The loadings plot is our variable map, and from this we can see that indeed principal component 1, explaining 82% of our variance, has a very large contribution from agriculture. So it's descriptive of agriculture versus service and industry, manufacturing and social personnel. These variables, which are close to each other, are correlated to each other. And they're also close to origin, close to 0, so they're not as important in describing and separating our samples from each other. The biplot brings the scores and loadings together, and from this we can relate the sample positions to the values from the variables. So indeed Turkey, which is extreme, has a larger value of agriculture. And you may recall when I first looked at those Euro work data and showed you the descriptive statistics and histograms, we saw that indeed there's a value that is extreme for agriculture. I did not go back to tie that to which sample it was, but indeed it is Turkey. It is the sample with a higher contribution of its GDP coming from agriculture than the other countries in the analysis. So now I'd like to briefly talk about partial least square regression, PLS. What is regression modeling? Well, in general, we use regression modeling when we'd like to be able to predict a value. So it may be the case that we don't have a direct way of making a measurement, or indeed we have a direct way and we'd like to model it and use that way to then predict future values from a measurement. So imagine if we wanted to measure the weight of samples but didn't have a balance. Well, one way that one could measure weight is to measure the displacement of a spring. But to know what that weight is, we would need to develop a calibration model. We would need to calibrate for this. So we do this by taking known samples, a calibration set, and relating that then to the mass of our known samples and what that spring displacement is. So this is our calibration set, and this is a univariate situation where we have a single variable that we're relating one versus the other. So we then do a linear regression to get a best linear fit for this, and we can write the equation then for our mass in terms of our spring displacement L. So we have a model. We could then measure a new sample, look at the response, here the length of our spring displacement, plug that value into our equation, and solve for our mass. So regression modeling is indeed doing this, and it can be for one variable shown here, or indeed multivariate, which is what we are talking about today. So in the univariate case, indeed, it's a simple least squares fit, but in the multivariate case, we want to then expand this to have many different variables, many different x's, and get the regression coefficients related to this, which we term B, the regression coefficients. So there are numerous regression methods available within the Unscrambler. We have MLR, PCR, and PLS, partial least square regression, also called projection to latent structures. And that's what I'll talk about and demonstrate today. And here with PLS, what we're doing is modeling the variance in X that best explains the variance in Y. So we're modeling two matrices simultaneously to come up with a model that can then give us the best fit of Y, our Y response, to X, our measured values. So I'd like to demonstrate this within the Unscrambler, developing a calibration model for ethanol in water from near-IR spectra. So I've imported the near-infrared spectra into the Unscrambler, and what I'd like to do now is relate the ethanol values, and we have samples that have ethanol ranging from 15 to 85 weight percent, and these are gravimetrically prepared samples. And I want to show the proof of concept of near-infrared for measurement to enable the development of an online monitoring method. And here I have near-infrared spectra exhibited, where I've highlighted a few of the spectral bands. And here we see that we have a very nice change in our signal across here, and this can be related to the different vibrational groups within the ethanol and water. So this is the important physics behind the measurement of the near-infrared, the ethanol and water. So going back to the Unscrambler, to that data set, so what I'd like to do, I'll close all my other tabs here and come back up to my data set here of my ethanol and water. And we already looked at a line plot of those, where we have the spectral data here. And what I'd like to do is within this not use the full spectrum, because I see that I have a noisy region here and I have a region that's almost flat here. I'd like to focus my analysis in on this part of the spectrum where I have the most signal and it's changing. So I'll again organize my data further. So I already have two column sets, one of the spectra, the full spectral range, but I'd like to create one that is a subset of that. So I will just highlight a column, any column, and then come to my define range. And I'm going to call this column set my analysis range. And because I've already studied this data quite a bit, I know what these columns I'd like to use for this are, and they are the columns that cover about 7,000 to 10,000 wave numbers. So these are column numbers 1072 to column number 2028. So you see that this is column number 1072, 78, 72 wave numbers over to, oops, here at about, about 4,200 wave numbers. Okay, so that's the column set that I'm going to create, and I created, and here it is within my navigator. So I'd like to now do a PLS regression on this. In order to do this, I come under Tasks, Analyze, Partial Least Square Regression. I need to now choose my model inputs, where now I'm defining what my predictors are, what my X data is, and here it is my matrix of my spectral data here. The rows that I'd like to use are my calibration samples, of which I have 15. For the columns, I'm going to use this analysis range, which entails 957 variables. And my response, they can be in the same matrix, but I need to have the right dimension. So here I have it in the same matrix, and it is 15 samples, the calibration samples. And the response variable, my y, is my ethanol concentration value. With spectral data, we typically don't apply weights, but of course we always do cross-validation. So we come to the Validation tab, we choose Cross-Validation radio button, click Setup, and indeed our cross-validation again will be random with 10 segments. And this is the cross-validation method we use when there are no special conditions or groups in our samples, if we don't have replicates. If we had replicates, those are not independent samples. So we would want to keep those out together and use perhaps systematic cross-validation if the samples were grouped in such a way that the replicates followed each other in our data matrix. So clicking OK and OK again, our PLS quickly runs and we can now view our results. So if I choose to view my plots, it brings up my PLS overview plots. Again, I have a new node added into my project navigator, now called PLS. I can rename that by right-clicking, choosing rename, and I can call this PLS ethanol if I'd like, or whatever name I may like. And we'll quickly take a look at our PLS regression overview. So as with a PCA, we have a score plot, which is a map of our samples. In this case, we have on our axes factor 1 versus factor 2. We now have two values shown here because we now are modeling the variance in X that explains the variance in Y. So we see with this data set, a very well-behaved data set, we have one factor, factor 1, wherein we're fully explaining 100% of the variance in X is explaining 99% of the variance in Y. So from these over 900 variables, we are using one factor, I should say, latent variable, to model that relationship. The regression coefficients are then basically the coefficients of each one of these variables. This is our model equation, graphically depicted. We can look at this. The regression coefficients come from the loadings, and we can look at the loadings, PLS loadings line. Here, because we have a single factor model, the regression coefficients and X loadings look exactly the same. If we had a two-factor model, it would then be the linear combination of our loadings for our first two factors, for instance. But in this case, indeed, it's a single factor model. These are our regression coefficients. We see that there's a very strong contribution in the negative way at about 150 wave numbers, as well as here at 7074. If you recall what our spectra look like, these are indeed the regions of our spectra where we have strong signal related to the OH. Which is indeed what we're looking to model in looking at this system. In our lower right quadrant, we have our predicted versus reference plot, and I can resize my plots. And here I have values in blue and red because I've run a cross-validation, so I have the calibration and cross-validation results here. I can toggle these on and off here in the toolbar. I can add the regression line to it. I can add the best fit line, the target line I mean, to this plot. So here we see that indeed these are the statistics of our PLS model. So this one factor model has a root mean square error of 1.8, and that would be weight percent, which is the unit of measure of our calibration values, and an R squared of 99.3. So we now have a model, and we'd like to see how well that model can predict on samples for which we have the reference values as a test of our model, so that we can test it and then feel confident and use the model on new samples in the future. So what we'd like to do now is do a prediction on this test set, these test samples, of which there are 14. So how do I do prediction? I come under Tasks, Predict, and I have a regression model, so I'd like to choose the regression. I select my model, and it must be in the same project where my data are, and here I have just one model, a PLS model. It is a single component model, and I'd like to do a full prediction on which data. Well, the data I'm going to use are my test samples. I need to have the same dimensionality of these data in terms of the number of variables as my model has, so I choose the columns analysis, 957 variables. And actually in this case I have the Y reference values for these samples, and I'll use those so that I can compare my results with what I know to be my results. So I've selected my model, told it which data to apply it to, and here I'm going to compare it to my Y reference as well. So clicking OK, I now get again a new node in my project navigator, Predict, and I have here my predicted value with deviation versus my samples. And in the lower part of this, I have the table of these values, wherein the deviation is actually a Unscrambler specific computation that is a comparison actually of your model that your sample that you're predicting to the samples that were used in your calibration set. So it is a very good measure of how similar or different your test samples are from your calibration samples. And a low deviation signifies that our samples are similar to those in the calibration set and that we can rely on our predicted results. So here we see the values for our ethanol prediction for each one of these 14 samples in my test set. I can also look at these results in another plot prediction, and I have predicted versus reference. And here we see that we have quite a good linear fit of this model, with the error of our model being quite close to what the error for my calibration set is. So what I've shown then is developing the PLS regression of the percent ethanol versus the near-infrared spectral data, wherein our regression coefficients indicate that the OH regions of our spectrum are important in modeling this system, and indeed that a single PLS factor is sufficient to model this. We then looked at predicting our test samples, and we see the predicted versus reference values, where we have the standard error of our prediction is quite close to that of our calibration model. When we look at our predicted values displayed with the deviations, we see that for some samples, those with the lower concentrations, we have a larger prediction deviation, but in general our deviations are quite small, meaning that these samples are similar to the samples that were used to develop our calibration model. So I'd like to leave with you information on what would be a suggested workflow for developing multivariate data analysis models. We should start by collecting our data with set sampling and acquisition, check our data, then make a model, check the model, apply our model to new samples to give us the results. And the different tools that we use along the way, it's a good idea to start with an experimental design using DOE. And then to check our data, indeed to plot our data, look at the statistics, do exploratory analysis of our data, including a principal component analysis. Then make a model using multivariate data analysis calibration, determining what type of model we're looking for. So for a regression model, we may use PLS as we use today. We do cross-validation as we develop our model, but we check our model by doing a validation with an independent test set of samples. And then to apply the model on new samples, we use the prediction function. And when we have a model that we'd like to use in real time, we can then use it within the Unscrambler process pulse, or indeed within the Unscrambler engines that may be embedded in software that you are using. So I hope that I've been able to tell you a little bit about multivariate analysis on the Unscrambler X today. And I'd like to encourage you to attend some of our training courses. We have some coming up here in Woodbridge, New Jersey next week, as well as scheduled in March. We have them in other regions as well, and you can check our website for details on the different dates for that. Today's webinar will be available off of our website, where you can also access other archived webinars by going to the Archived Webinars tab. From our website, you can also sign up for our Camo newsletter, which includes tips and tricks on how to use the Unscrambler and some scientific news about different applications of the Unscrambler. So with that, I'll be happy to answer questions. And if you'd like to, please type those into the chat log. I'll try to address the questions as I read through them. There's a question about neural networks, and indeed that is not used within the Unscrambler. The regression methods that we have within the Unscrambler, we have under Tasks, Analyze, and these are all the analyses tools that we have. So we have statistics, we have single matrix exploratory data analysis tools, we have different regression methods, including LPLS, and we do have, in addition to classification by SIMCA and partially square discriminant analysis, we have linear discriminant analysis and support vector machine classification. We also do have the full design of experiments within the Unscrambler. There's a question on getting RPD and CV values. That is actually something that you can calculate indeed from your data. And I don't have the equations right here on the top of my head, but I could refer you, if you drop me an email, to literature on how to compute those. That is relative to your values and the range of values that you're using within your calibration set. Question on changing colors in groupings and plots. Indeed, I'll be happy to show you that. Let me come back to going here to this EuroWork PCA model. So if I come to my PCA model here, here's my scores plot where I added sample grouping, which color-coded my data. So if I'd like to change the color coding of this, or indeed to add sample groupings, I right-click and choose sample grouping. So I would choose what type of sample groups I'd like, and here what I did, just to show you this again, is I didn't have any available row sets here. If I were using this data set, I have some row sets. But in the EuroWork data, I didn't create row sets, but I can create information from my category variable. So I clicked on, going again slowly, I clicked on Define. I highlighted my category variable column, clicked OK, then I choose Create Row Sets. So it will create row sets for each one of the category variables in the column I've selected. I move those over to the marker settings, and here is where I can change the colors. So here I can change the colors of what these markings will be. I can change what the symbol will look like. I can change the size of the symbol and so forth. Likewise here, oh, that doesn't make sense to have two greens. I can change whether or not I'd like to use the group name as a label, whether I'd like to separate samples with colors, symbols, or both, which is the default and the one I prefer to use. So I then click Apply, and I have this now. Of course, once you have a plot, you can copy and paste that plot into another application if you'd like, or indeed save the plot into different types of graphical formats. So that is available to you as well. How do I identify which peaks in my PCA analysis are related to my data set? Well, in this example, I did a PLS analysis actually with my spectral data, but let me just go ahead and do a PCA on the same data. the interpretation is analogous. So if I choose my spectral data and go Tasks, Analyze, and do a PCA analysis, I would choose, now I'll use all my samples, and again, just my analysis region. Clicking OK, I get my PCA results here where I have my scores plot, my map of my samples, and I can indeed group these samples based on my available row sets, which include my calibration and test samples. And I see that I have a nice overlap of samples here. And then which peaks are important? Then I look at my loadings. And here indeed I see that these are the loadings. My loadings are the coefficients of each one of my variables in my model. So when I have a large coefficient, that means that those are the important peaks. And for this data set, I actually know, and it's important that we go back to the science of this, I know that these are the peaks that are related to the OH bands in my near-infrared spectra. So that is a very important part of our data interpretation within multivariate analysis. So we have time for just a few more questions. How do you calculate the percent variance? Well, indeed, this is how the data are looking at the analysis, and what we're showing is the percent variance that is explained, and it is related to, indeed, the eigenvectors and eigenvalues of your data that are computed by doing the principal component analysis. Someone is dealing with some elemental data where you have very different measures of your different, I guess it's XRF data perhaps, for the different elements. What I would recommend doing in that case is to apply a transform to the data. And to apply a transform, we go Tasks, Transform. And with that type of data, it may be appropriate to center and scale the data. Or indeed, you could apply a logarithmic transformation. So transform, and I'm looking for it here in the menu because I don't often apply these. You can do a compute general, and from this you can choose different types of transformations as well. So it is a good idea to scale the data when you have very different values across the different variables that you're measuring. There's a question on different variations of PLS method within the Unscrambler. Indeed, if you come under Tasks, Analyze, Partial Least Square Regression, we do have some different algorithms that are available if you go to the Algorithms tab. The Nepal's algorithm is the default algorithm and is that was published by Martins and Nyes and is the basis of the Unscrambler 9.8 and previous versions. But we do have other algorithms available as well. So with that, I'd like to thank you all again for joining today's webinar. I'd like to welcome you to attend our courses and visit our website and be in touch if there are any other information that we can provide for you in the future. Thank you very much. Bye-bye.